I feel like Hammett parameters and analysis is best illustrated with some examples. So I'm going to give you some examples from the book. Here is something that is called an aryl carbamate ester. Carbamates are functional groups where you have a carbonyl carbon bonded to an oxygen and to a carbon. And it is known that if you have an aryl carbamate ester in which the nitrogen is just bonded to 2 protons, your mechanism tends to go through this pathway where you kick off the leaving group in a slow rate determining step. And that generates the phenolate leaving group. And you've got the X substituent there. So you can see where we're going in terms of the Hammett analysis. The intermediate you form on the other side is actually called an isocyanate. And I should actually mention that the aryl carbamate gets deprotonated first. I'm sorry. You get the isocyanate as a product, and then water can come in and you get the carbamic acid, which itself can later decarboxylate to give you an amino group. Well, and I guess in this case, since we've got 2 protons, where the heck is that R group coming from? I apologize for my strangeness here. I'm getting confused because your text didn't actually show the proton. It just put an R group there, and that was confusing. But anyway, why would you want to do this in the first place? It seems like you're going from something more complicated to something way more simple, and I got nothing. I don't know why. There's an alternative pathway that can occur when you have some kind of R group on the nitrogen, so something that's not proton. And in this case, the mechanism actually goes through more of a addition to carbonyls type mechanism, where you have attack of the carbonyl carbon to give you the familiar tetrahedral intermediate. This would be the rate determining step. And so let's see. Got to give myself enough space here. So here's your tetrahedral intermediate, which is going to collapse to give you the carbamic acid. We'll just put an R there, I guess, to be as general as possible. And I guess I'm going to say that R here equals H or R, so it's kind of a recursive definition. All right, so you can do the Hammett analysis by changing the substituents. And remember, we use those sigma values as independent variables, and then we measure the rate. And then we plot the rate, the log of the rate versus ratio of, let's see, we plot log of rate for substituent X over rate for proton versus sigma. We get a plot with a slope rho. In the case of pathway A, rho is equal to 3. In the case of pathway B, rho is equal to 1. Does that make sense? Why is rho different for these two pathways? And you got to think about what the rate determining step is. Any guesses? What do you think? Go ahead, Isabella.
Well, on the one where rho is 3, the rate determining step is the leading. So if it's a more stable negative charge, it would be faster.
Okay. When the rate determining step is this group with the substituent leaves and the negative charge is there and it's possibly resonance stabilized by that group, then you would expect that substituent to matter more. And remember, rho tells you how much more does that substituent matter in this reaction versus in the benzoic acid deprotonation reaction. That's the reference reaction here. In contrast with B, you're still forming a negative charge, but it's kind of far away, or it's farther away from where the substituent is. Yeah?
So the isocyanic acid intermediate is not stable?
The isocyanate, this intermediate, the carbamic acid or something like that, I think it spontaneously decarboxylates. I don't know, though.
Okay.
Yeah.
Isocyanate.
Actually, it makes sense that it should spontaneously decarboxylate. Somebody should have raised their hand and called me a disgrace of a professor for saying that. This is how Bach and FMOC protecting groups work. So yes, naturally, the carbamic acids are not stable. They spontaneously decarboxylate. For shame. Oh well. That wasn't shame on any of you for asking the question. That was shame on me for hemming and hawing. Oh well, we're all human. I'm not actually sad about it. I'm smiling underneath here. You can't see. One of the interesting things that I won't show you is that, but it's in an example, well, it's in one of these going deeper connection highlights in your text, is that a group evolved an antibody that was an antibody that would bind an intermediate that looked like this. It wasn't this one because, of course, this isn't stable, but it was some kind of phosphate-containing molecule, and they found that by making that antibody bind a structure like this, they were able to take the starting material that would have preferred the A pathway and make it go through the B pathway. We'll learn more about catalysis, I think, in Chapter 9, but one of the things that catalysts do is they bind the transition state more favorably than they bind the starting material or the products, and that's they used a Hammett analysis to demonstrate that their new catalyst had changed the mechanism of the reaction. All right, so I think we mentioned last time that because the original Hammett parameters had been derived from, say, this reaction, and you were considering the impact of, I'm not showing you the deprotonation reaction, but the impact of that X group on the stability of this conjugate base, and that negative charge isn't directly conjugated to that X group. So you're sort of seeing a mixture of resonance and inductive effects, and in particular, if you change the substitution from para to meta, there's a mixture of those things. So people have been interested in separating out resonance from inductive effects. And so to do that, they've simply changed the reference reaction. So parameter sigma minus relates to the ability of a substituent X group to stabilize a negative charge by resonance, and that's why there's the sigma minus there. The reference reaction in this case is phenol deprotonation, actually. So this is kind of boring and easy to measure. So the phenolate ion, if you had the right group here, you could stabilize that by resonance. I'm not going to draw the resonance structure because I think you could probably figure out how if X equals nitro, that negative charge can be delocalized. So some example values for sigma minus include, and they're mostly defined for electron withdrawing groups. And in this case, larger and more positive sigma minus means better at stabilizing a negative charge. So phenyl group at the X position is only moderately stabilizing of negative charges. However, carboxylic acid has a sigma value of 0.73. That means if you put the carboxylic acid at this position, the ionization is almost 10 times more favorable or faster. I'm not sure whether this is defined for rates or equilibrium constants. In particular, regular players in terms of resonance withdrawing groups, cyano is quite good. And then nitro. The squiggly line means what we've attached these groups to, 1.23. So that's another scale, and I guess we could go look back at the previous notes to just get a sense for what the sigma value for nitro was. So that's, yes?
Okay, maybe I shouldn't interrupt too much, but how do people decide whether they're going to use sigma or sigma minus for their comparison?
So how do people decide whether they're going to use sigma or sigma minus for their comparison? The answer is you use the sigma values like they're independent variables to test whether your transition state involves that kind of thing. So you would use a sigma minus if you thought the most important thing in this transition state is resonance stabilization of a negative charge. And then you'd see whether you get a correlation with these sigma values and the reaction rates. And if it was 1 or greater than 1, then you could say, oh, or if the slope was 1 or greater than 1, then you could say, oh, this reaction is at least as sensitive or more sensitive to the substituent than the phenolate ionization, and therefore likely in the transition state of the rate determining step, there's a buildup of negative charge where it can be stabilized by resonance. So it's a way to test hypotheses. And it's not, you're not going to go measure these values. You're going to look them up in a table and then do the experiment on your reaction of interest. Others? An analogous set of parameters exist for stabilizing positive charges by resonance. The reaction here is the leaving of chloride from this tertiary carbon to give you the carbocation. I'm not going to draw the potential resonance structures of any of these groups. Hopefully you can see that if this was a lone pair, if this was a heteroatom that had lone pairs on it, you could donate electron density into the ring and finally to the place with the positive charge. If you can't see that that's the case, go look it up in your book or give it a try. These sigma plus parameters relate to the ability of a substituent to stabilize a positive charge. In order to have them agree in sign with the regular Hammett sigma values, negative values of sigma plus mean the ability to stabilize, better stabilizing of positive charge. So examples of groups that have sizable sigma plus values are the aniline, and if you compare this value of minus 1.3 to what we saw before for just the regular Hammett parameter, the regular Hammett parameter was minus 0.6 or minus 0.7. The sigma plus, which is exclusively resonance, is more than that. So what that tells you is nitrogen's a better resonance donor than the Hammett parameter would have led you to believe. And there's some other values of interest. Methoxy is an example, minus 0.8. Not as good as nitrogen. Again, that makes sense based on your understanding of electronegativity. Go ahead.
So in order to use these values, wouldn't you need to have a tertiary carbocation to avoid changing too many variables? Or?
Would you need to have a tertiary carbocation in order to use these values? I don't think so. You would use these values to interrogate, is there a buildup of positive charge in the transition state? Yeah. And you might expect if you were doing this with like a secondary carbocation, you might expect a rho value, a slope of greater than 1, meaning it's even more sensitive to the identity of the substituent. Yeah. Okay. Other questions? Sometimes using these values, plotting against rates of reaction, can give you an indication of a shift in mechanism. So there's an example from your book that's very similar to the one I just showed you. And this is, I guess, Kim, your question was great because it sort of leads right into this. I'm going to put the X right here to indicate that there's going to be both ortho and para substituents included in this analysis. Here you've got a leaving group. And the people that did this study did the reaction using azide as a nucleophile, but in some protic solvent that could potentially compete with azide in the substitution reaction. And the products that they observed were either the azido product or the what is called the solvolysis product. This is the product that occurs from the solvent acting as the nucleophile. It's thought in general that the azido product, well, you could get the azido product either from an SN2 reaction or from an SN1 reaction. And then you could get the solvolysis product mostly from an SN1 type reaction because the solvent is not a good nucleophile, whereas azide is. So they plotted the logarithm of the rate ratio for forming azide divided by forming the solvent product. So this is relative rates here of forming either of these two products. And then they plotted those numbers, and the log is over 7 orders of magnitude. And then they plotted that versus sigma plus of the various substituents. And I'm just sort of trying to give you a sense for what this plot looked like. So up here you have the para dimethylamino group. Then sort of down here is the para methoxy and para methylthiol. Getting closer to sigma plus equals 0, you have para phenoxy, so that's using this as your substituent. You're going from things that are better resonance donors to things that are worse resonance donors. You get here down to para-methyl, and there's basically no difference in the rate of the reaction for substitution with azide versus solvent. And you can sort of plot a straight line through these points. That's not very good linear regression. You go to para-fluoro, and there's still no change. And then you start adding other things like meta-methoxy or meta-bromo, or withdrawing groups, para-cyano and para-nitro. And again, these are my crude attempt at showing data because I didn't take the time to copy and paste the graph from the book. And you've got another line here. So you've got a negative slope here. You've got a positive slope here. What does this tell you?
as you decrease the ability of the group to donate electron density via resonance, the amount of azide versus solvent goes down till you get to 1-to-1. And then as you continue to make the substituent a poorer donor and in fact a better withdrawer, now your ratio of azide goes up again. So that's weird. What do you think's going on there? Go ahead, Dakota.
Is the resonance donation by the leaving group? Does that make it harder for the group to come off and therefore encourage SN2?
So resonance donation here is by the substituent, and in these cases the para-substituent, but the leaving group is leaving from here, from the benzyl position. Go ahead, Kim.
I would assume that donor groups would make it easier for the leaving group to leave because it'll stabilize the carbocation that's left behind.
Okay.
But as you get withdrawer groups, it makes it harder for the leaving group to leave, which is why the
Okay.
product is more prevalent because it's happening to an SN2.
So you're saying over here where you've got more stable carbocations, the mechanism is probably SN1 because the leaving group can leave. But if the mechanism's SN1, why does azide still beat solvent?
It's more likely to come in.
I guess azide is inarguably the better nucleophile.
Yeah.
So azide's the better nucleophile, so it can outcompete the solvent. It looks like it can outcompete the solvent better when the leaving group has left. And maybe that makes sense because if the leaving group is mostly gone, there's more space for the azide to come in than as if it's only partially gone. As you get to less and less stable carbocations, and remember, you're not changing the resonance of the ring, you're just changing the substituent on the ring. So this is still a resonance stabilized carbocation in the mechanism, but you get to more of a 1-to-1 ratio, sort of bottoming out. But then as you go here, Kim, you're right, you're making a carbocation way less stable such that you're favoring the SN2 mechanism. And in the SN2 mechanism, the strongest nucleophile starts to win again. So it's nuanced and it's difficult it's certainly not one or the other. Remember, we're using these substituents to basically interrogate a potential energy landscape. And what we're seeing is that this reaction mechanism, depending on what you've got out here, can go from something that's pretty well SN1-like to something that's intermediate and then perhaps more SN2-like. Yeah?
So then if it's an SN1.5 reaction, how is the solvent able to have more of an advantage?
Well, if it's sort of here, why does the solvent increase in advantage? Statistically, the solvent should have an advantage.
Then why doesn't it for SN1?
I don't know. That's an interesting question, and I would say that this is probably not product ratios but rates.
Okay.
And so in the case of rates, the more reactive nucleophile reacts faster.
Okay.
I don't know. That's a good question, but because what you're not seeing is negative values here where the solvent ever wins. It gets down to 1-to-1, but the solvent never wins here. Follow-up question? I'm not sure that's Makes a huge amount of sense. I mean, it is surprising to me that the more SN1-like the mechanism is, the azide wins either way, whether it's SN1 or SN2. I think it's where you get to sort of these intermediate values that then you're not totally forming a carbocation, but you're also not totally having the nucleophile come in yet, and that appears to be the regime under which the solvent can start to compete. All right. There are a bunch of other linear free energy relationships in the chapter, and I start to lose interest when they start having hyphenated names. I don't know why, other than there's just too much to remember. So you can certainly go back and look at the text. There's linear free energy relationships with solvent. There's linear free energy relationships for sterics. We're not going to talk about them or spend a lot of time on them at all. The one that I did want to talk about was some linear free energy relationships for nucleophilicity and leaving group ability. Your text calls electrophilicity nucleofugality, which talks about an electrophile being a nucleofuge, which sounds like something going on. It sounds like some sort of equipment illicitly imported into Iran for uranium enrichment. So I'm not going to use that word. I don't know why. But, we talked a lot in undergrad or OChem about what makes a good nucleophile good. And to a first approximation, one of the first things we said is, well, good nucleophiles are conjugate bases of really, really weak acids. And so the early attempts to correlate nucleophilicity with a linear free energy relationship involved taking the log of the rate of a reaction under study and plotting it against the pKa of the conjugate acid of the nucleophile. And then there would be a slope called beta, and because this involves nucleophiles, it's beta sub nuc. And then there would be some constant, which doesn't have a physical meaning, so you don't need to worry about it. And you would plot the rate of your reaction versus the pKa of the conjugate acid, and you would get this beta, which is a sensitivity factor, which tells you how much are changes in basicity, or pKa of the conjugate acid, reflected in nucleophilicity. And by nucleophilicity, we mean speed of reaction. How fast does this nucleophile react? Because you're dealing with pKa's, the reference reaction is water deprotonation, but this tends to hold, this linear free energy relationship tends to work if you use, if the nucleophiles are similar electronically and sterically. Can you think of a situation where this linear free energy relationship doesn't hold? Can you think of some comparisons that where a nucleophile that has that is less basic is actually the better nucleophile? Go ahead.
We learned that sterically bulky bases are not good nucleophiles.
Yeah, right. So if you were to do tert-butoxide pKa 19 of conjugate acid versus ethoxide pKa 16, the lower pKa one is actually the better nucleophile. So this kind of analysis, this kind of comparison works, but only when you're not changing sterics or electronics. Another classic example where this fails is like iodide versus fluoride in protic solvents. And we'll talk about a lot of these other factors of nucleophilicity. So because nucleophilicity doesn't always track with pKa, you got to be careful in terms of how you apply the analysis. However, if you want to do leaving group ability, it tracks a lot better with pKa of conjugate acids. So rate of leaving group leaving plotted versus the pKa of the conjugate acid of the leaving group plus some constant. Again, you get a linear relationship, and again, you have a sensitivity factor. And you can measure both beta nucleophile and beta leaving group in the same reaction to get a sense for the relative amounts of nucleophilic attack versus departure in the transition, leaving group departure in the transition state. One example of a case where this was used was in understanding ATP hydrolysis. And this is not catalyzed and uncatalyzed ATP hydrolysis. You're not going to make me draw the whole thing of ATP, are you?
Draw the whole thing, Josh. Takes more time.
If it were not COVID, I would stick my tongue out and blow a raspberry. But since that's inappropriate in times like these, I will restrain myself. So alcohol, phosphorylation of an alcohol with ATP gives you the phosphoester and ADP. And the question was, what is the transition state like? Is it an SN2 kind of reaction where the alcohol attacks the terminal phosphate group and the leaving group leaves in the same step? To what degree does the nucleophile attack before the leaving group, and I'll just highlight the leaving group here. To what extent does the nucleophile attack before the leaving group leaves? All right. And understanding this is important because anytime you want to know how enzymes work, you also have to understand how the uncatalyzed reaction works. So here's your leaving group, here's your nucleophile. So they did a study on this reaction by varying the alcohol that was getting phosphorylated, and then they plotted, so they varied alcohol pKa's basically, and then they plotted the rate of the reaction versus the pKa of the alcohol. And the beta factor, the sensitivity factor, was only 0.07, which, if you look at that, that means there's essentially no relationship between the pKa of the nucleophile's conjugate acid and the rate of reaction. All right? Meaning, potentially, okay, let me back up. What does that tell you about the transition state? What does that tell you about the reaction if the basicity of the nucleophile doesn't matter a lot for reaction rate? Go ahead.
The nucleophile attacking is not part of the rate of
Okay, the nucleophile attacking is not part of the rate determining step. Now, what if you found that it was first order in the nucleophile, but the basicity of the nucleophile didn't matter? I don't know either. It might mean that the transition state involves the nucleophile, but the nucleophile is not, the new bond is not formed very much. Right? There's a continuum between totally formed and not even kind of formed, and we're here out in infinity. And if there's not much of a relationship, the conclusion was that there's not much nucleophile phosphorus bond forming in the transition state. Now, I actually don't know whether the reaction's first order in the nucleophile or not. Since the product involves the nucleophile, you'd think it would have to be involved, but maybe it depends on concentrations like we learned about in chapter 7. They did the same analysis for reactions where they varied the leaving group structure. They didn't stick with ATP, but they chose other phosphoanhydrides, I think. And this is published work from the 90s, so I think if we wanted to, we could go back and look at it. What they found, though, by plotting the log of the reaction versus the pKa of the leaving group's conjugate acid was that the structure of the leaving group was highly influential. Okay? Better leaving groups accelerated the reaction. And what that tells you is that the reaction is extremely sensitive to leaving group structure. So the conclusion, putting all of this together, was that in the transition state of the rate determining step, leaving group is significantly departed, whereas nucleophile isn't quite there yet. And they envisioned some kind of transition state that would look kind of like this. They called it almost a dissociative mechanism, where the phosphate sort of pops off the ADP, and then the nucleophile comes in. Almost SN1-like, basically, at the phosphorus. And again, that's for the hydrolysis in solution. And now you're starting to maybe get an idea of what an enzyme might do, right? If the uncatalyzed reaction is almost SN1-like, could you make this reaction faster by making the nucleophile matter? I don't know. And we'll have to look at that as we start talking about catalysis. There's another nucleophilicity. Any questions about that we should talk about? There are other factors that influence nucleophilicity, and these are familiar to you. Your book talks about them in some detail, but I just want to mention them here and then refer you to that part of the book. Of course, we've got basicity that we've just covered, where you're looking at the pKa of the conjugate acid. But there's also this issue of how solvated the nucleophile is. So-called naked nucleophiles are more nucleophilic. That means if you have a nucleophile that is less solvated or larger, it can be way more nucleophilic. Because remember, in a reaction where a nucleophile is attacking something, it's got to get solvent molecules out of the way. So if you have, say, an anion in a solvent that doesn't interact well with anions, then it's more, that anion could be more reactive. Let's see, polarizability is another issue. This is the ability of a nucleophile to accommodate changes in the shape of its electron cloud. If you're more able to accommodate changes in shape, I'm not spelling words correctly, accommodate changes in shape, then you're a better nucleophile. This is why iodide is better than chloride as a nucleophile. This is why thiols are better nucleophiles than alcohols. They're more polarizable. And there's some solvation differences as well. And then finally, shape overall. This is something I didn't appreciate, but linear nucleophiles are more reactive because they're like torpedoes. So if you've got azide, or cyanide. These are linear nucleophiles that don't have to worry as much about sterics as they go in to attack an sp3 hybridized carbon. Now, there is a scale for nucleophilicity that reflects all of these factors, and it's based on, this is the one hyphenated one that I'm going to include here, although I really don't care that you know about the Swain-Scott nucleophilicity parameters. I've never heard anybody mention that in a talk. If you want to drop names and sound fancy, focus on naming heterocycles without missing a beat. If you can say oxazolidenone or that's all I got actually, or tetrazole or something like that, people think that that's impressive, but I've never heard anybody try to impress others with talking about the Swain-Scott nucleophilicity scale. If you're going to do it, please be swirling a martini at the same time as you mention it. I think that will make you look fancy. So the reference reaction here is methyl iodide with water to give you methanol and HI. And so they define the parameters by taking the log for this reaction of methyl iodide reacting with nucleophile X divided by the rate for methyl iodide reacting with water. And you plot and you take those rates for each different nucleophile and you get parameter nx. This is like a Hammett parameter, but it's n for nucleophilicity. And then you use that as your independent variable for your new reaction of choice. You plot log for your new reaction with nucleophile X versus log for nucleophile water. You plot that versus these nucleophilicity parameters and you get a sensitivity factor, which tells you how sensitive your reaction is to the structure of the nucleophile. And I just want to show you a couple of nucleophiles and what the Swain-Scott parameters are versus the pKa of the conjugate acid. And this will start to reflect a lot of the things you know by experience. So fluoride, pKa of conjugate base 3.5-ish. Swain-Scott parameter 2.7. Chloride, pKa of conjugate acid -6. Swain-Scott parameter 4.4. Right away, chloride's a better nucleophile than fluoride is under these conditions because, and it's better than you would expect from the pKa differences, and that's because of chloride's larger size and increased polarizability. Bromide's even better, even though its conjugate acid is even more acidic. So this is the number scale that you may have been wishing for in 351 when you were trying to figure out what is a good nucleophile and what is not. And when I taught 351, I tried to give people some ballpark of pKa values of conjugate acids that made good nucleophiles good versus bad. But this is what you were really looking for. Azide is about as good as bromide, even though its conjugate acid is not that strong, or rather, even though its conjugate acid is stronger than a lot of other things. Water and methanol have 0, of course 0, because water is the reference nucleophile, pKa -1.7. Just a couple others, methoxide, 6.3 on the Swain-Scott scale. So just look at that. Azide is just about as nucleophilic as methoxide, even though there's a 10 billion-fold difference in their basicity. pK of conjugate acid. Sorry. Yeah. But then compare that to the corresponding thiolate Oh, dang it. They don't have it, do they? I'm just going to write more stuff. Sorry. To make the comparison good, here is phenolate anion. Swain-Scott parameter around 5.8, pKa of conjugate acid like 10. Another comparison again where azide is just about the same in nucleophilicity, even though it's so much weaker of a base. Let's go to the thiophenolate, nucleophilicity 9.9 versus pKa of conjugate acid 7, right? This is 1,000 times less basic than phenoxide, but it's like almost 10,000 times more nucleophilic, again, because of polarizability. So I thought this was cool. I mean, I'm not suggesting that you memorize Swain-Scott nucleophilicity parameters, but I thought the comparison with pKa was kind of useful and how nicely this scale summarizes all of these factors that we've talked about. So maybe in the future, if you're ever TAing an undergraduate class, you could say something like, well, you know that with pKa values, you can get a good sense of nucleophilicity, but you'll really be led astray, and you'd be better off using the Swain-Scott nucleophilicity parameters. And then you can get, for your teaching, the kinds of teacher ratings I get for my teaching, which involves criticism of all of my jokes, dang it. All right. That basically takes us through Chapter 8. There's an important concept at the end that talks about why linear free energy relationships work, and it's a brief little gem about something called entropy-enthalpy compensation, which is an important concept to get. So I think we'll start with that next time. And then we're going to move on to either Chapter 9 or Chapter 10. I'm not sure. So stay tuned. And have a good day. See you, Mario.